Good morning, everybody. All right. Announcements. I don't really have a whole lot. Obviously, test number 5 is now done, so we just have one thing left to do on the 16th. Um, so today we're going to keep going on new material. I'm hoping to get as much of it, if not all of it, done today, but probably not all. So we will have a little bit of time on Thursday finishing new material, but certainly not the whole class. So my plan for Thursday, other than just finishing off the material, is to um, is to um, go over whatever questions that you have. So that's my plan on Thursday. So what I don't really want to call it a review, because I mean you've spent 3 months listening to the things I've wanted to talk about. I want to be answering whatever questions you have. I'll obviously have something prepared just in case, but I find reviews work a lot better if I'm answering your questions versus you answering mine. So that's my plan for the Thursday once we are done the material. That is my plan for Thursday. So hopefully that makes sense. So I know at that point we can. I'm not pre-marking people's tests. Um, the um, where was I going with that? Yeah, so that's my plan for Thursday. Um, so if you want, you can. That means you can type out questions in the chat during class. But if you want to ask a question where that might be difficult, if it is from the textbook, obviously you could just put the question number in the textbook. But otherwise, feel free to also send me questions ahead of time that you want me to go over in class, and we can do that as well. All right. How many questions on the file? I mean, I wouldn't know enough that it could be done in 2 hours. We haven't made up the test yet. I don't have an answer for that at this point. More information about the exam will be flowing later on this week or early next week. All right. Feel free to keep your questions coming if you have any. If not, there should be a question, I believe, on your screen in terms of eigenvalues and eigenvector and eigenspaces. So it's right there in front of you. Feel free to get started. Yeah, that's a hard question for me to answer. I don't have your test in front of me. I can't say how many grades I think somebody's going to be losing based off of mistakes. Without being able to see the test, I can't really answer that question beyond wild speculation, which serves no purpose, because if I say, oh, you should lose 1 mark, and then the marker makes a different decision, that then the student is obviously upset, and then I would go and look at their page, and I'm like, oh yeah, I see based off that mistake that's why the marker did what they did. So that's why I say I don't pre-mark tests. It's because without being able to look at your test and seeing it in complete context, there's really no way for me to answer that question in a way definitive enough for me to be confident in my answer. All right, so this is our first question about discussing a lot of ums and abouts for me today. Discussing how to find eigenvalues and eigenvectors of a transformation versus the eigenvalues and eigenspaces of a matrix. So other than the real quick way we can flip between the two, what are we trying to do geometrically? So the question said find it algebraically and geometrically. So we'll start geometrically. So geometrically speaking, what are eigenvalues and eigenvectors? So what are the eigenvalues and eigenvectors? Specifically the eigenvectors. Geometrically, what does it mean to be an eigenvector for a transformation? What does it mean to be an eigenvector for a transformation? It's a scalar multiple of v, which is what it means algebraically. Geometrically speaking, it means that it's parallel. It means what goes into the transformation is parallel to what comes out of the transformation. So based on the vector that I've drawn here, we're reflecting about y equals x. Is the vector here's t of v, reflected about y equals x, is the vector as I've drawn it an eigenvector? Is what goes into it and what comes out of that transformation parallel to each other? The vector I've drawn. No, no, of course not. So is there any vector that we could draw that will be parallel once we've done the reflection? And if so, what would the eigenvalue be? So yeah, the first thing to note is that we could in fact just draw any vector that's parallel to this line. So if v is parallel to the line, then what's t of v equal to? So what is if we put a vector that's on the line into the transformation, what's the output? Just v itself. So what is the eigenvalue? So what's our eigenvalue going to be? Anyone want to back that up? Yeah, absolutely. Typically, we wouldn't write t of v is equal to 1 times v, but it is. And that's the constant we're looking for. In other words, lambda is equal to 1. And what's the vector going to be? Because being on the line is all nice and geometric, but what's the components going to be? So what's a vector like that? Again, there's infinitely many. But they're all vectors that are parallel to 1, 1. So in general, TT, in other words, anything where y is equal to x, because it's on the line y is equal to x. So here's our eigenvectors. Technically, if t is not 0, so that's really our eigenspace. So our eigenspace is everything of the form TT, where lambda is equal to 1. So that's one example of an eigenvalue with its eigenspace that we can find geometrically. Yeah, that's a bracket. It's not c lambda. Is there any other vector? Is there any other vector that reflected would be parallel, other than something that's parallel to y equals x? Yeah, if we had something that's perpendicular to y equals x. So if our vector v is over here, what happens when we reflected about y equals x. So if that v was that vector, reflecting it about y equals x makes it go into the opposite direction. So now t of v is over here. In which case, well, someone already answered it. What's t of v? T of v is equal to negative v. So what's our eigenvalue? What's the constant in front of the v? Yeah, so our lambda is equal to -1. And what would a vector, this is a little bit harder, what would be a vector that's perpendicular to y equals x? Although, while a bit more complicated, we did talk about that in chapter 3. Yeah, remember, if we had something of the form ax plus by equals 0, then AB was perpendicular to it. So if we think of this as being, negative x plus y equals 0, then a vector perpendicular to it is -1, 1. In other words, it's anything of the form negative tt, which you could either figure out directly or note that it has to be perpendicular to y equals x, so it has to be perpendicular to what we already found before. All right, so there we go. And this is how we can find eigenspaces geometrically. Obviously, it's a lot of, what is this situation? What is that situation? So it's not a perfect system. But there is a geometric idea of what we're trying to do here. All right, anyway, let's get back to the algebra. So let's see if this actually corresponds to what we're going to see algebraically. What about t negative t? Great question. Is t negative t really any different than negative tt? So what would be an example of a vector of this form, t negative t? Some people were saying t negative t or saying 1 negative 1, so fair enough, I should have addressed that. Could someone give me an example of a vector, t negative t? Any real number. T is any real number. Because there's infinitely many of these vectors. Right? I drew one, but I could change the length. So it's any multiple of -1, 1. So can someone give me an example other than, back to this one, other than 1 negative 1? Can someone give me an example of a vector that's parallel? Or I guess in this case perpendicular, just a specific example. Oh, I guess unless you're using the, yeah. So for example, we could do 2 negative 2. Is 2 negative 2 covered by this? Yeah, which t? Right. Right, so this eigenspace and this eigenspace are the same eigenspace. They're the same because t can be any real number. So for one of them, t is 2, the other one, t is negative 2, but they will always give us the same thing. So my point being is if you had said, instead of saying negative tt, like I did, if you did t negative t, they're both completely correct. They both actually give us the exact same vectors, even if they might look a little bit different. All right, anyway, so that was the geometric way of handling it. So let's think of this algebraically and do the kind of ideas that we were talking about on Thursday. Now, when we were doing this on Thursday, we needed a matrix. This was bad. We wanted it to be A times V, or X, technically. Let me be consistent and use it with X, not that it matters. We didn't want T of X. We wanted A times X to be equal to lambda X. This is what we did on Thursday. So what can we do here? How can we find this matrix? We were given a transformation. How do we find that matrix? We can use the fact that any linear transformation can always be written as matrix multiplication. So in actuality, whether we're doing it as matrix multiplication or a linear transformation, it's really the same thing. And what did we call the matrix A? Bingo, yeah, we called it the standard matrix. In other words, we can find eigenvalues and eigenvectors for a transformation by finding the eigenvalues and eigenvectors for its standard matrix. And then it's exactly the same as the type of questions we were doing last week. All right. And what is the standard matrix for this particular reflection? We actually did this example in 4.9. What was the standard matrix? 1 0 or 0 1 1 0. In other words, if we use the standard matrix, then doing a transformation is the same as matrix multiplication, and we spent a lot of time last week doing that. All right, so any questions about those ideas before we just do another eigenvalue, eigenspace question? All right, so how do we find the eigenvalues and eigenvectors of a matrix? In this case, it's 2 by 2, so it'll be relatively easy as compared to some of the 3 by 3s we did. So we said 0 equal to, well, the determinant of lambda I minus A. So that's lambda negative 1 lambda. It's lambda I minus A. And it's a 2 by 2, so what's that? Lambda squared minus 1. So we got our characteristic polynomial, lambda squared minus 1 equal to 0. How do we solve that equation? Yeah, plus or minus 1. We can factor this thing, lambda plus 1, lambda minus 1. So we get lambda is equal to negative 1 from the first factor. Oh, yeah. Question said, find it geometrically. So we did it geometrically. Now we're using the methods from this section, the whole characteristic polynomial thing to do it. And we're going to see that we get the same answer. All right, so surprise, surprise, we got the exact same two eigenvalues that we got when we did it geometrically, and we'll find our eigenvectors and hopefully see that we get the same thing as well. All right, but any questions about how we found our eigenvalues? All right, so lambda equals 1. So again, this isn't our first one. We plug lambda equals 1 into our matrix, solve where it's, whoops, that's a lie. Solve where it's equal to 0. So 1, negative 1, negative 1, 1. So now we're trying to find the solutions to lambda I minus A x equals 0. Nothing different than what we did on Thursday. We saw examples of this on Thursday. You probably saw some in your tutorial as well. And now it's just solving a system of equations, which we have done a whole lot since chapter 1. Fortunately, this is also a pretty quick one. We get a row of zeros at the bottom, as we've mentioned and give reasons for. That should happen every single time. So how do we get our solutions from this reduced row echelon form? Sounds good. X2 is our parameter because it doesn't have a leading 1. X1 minus X2 is 0 from that first row, which would say X1 is equal to T. And so our eigenspace, whether you write it as a column or whether you write it as just a normal row vector, and surprise, surprise, we got the exact same vectors that we got when we did it geometrically. And we could do the same thing with -1. This is the worst Greek letter ever. Let me fix that up. All right. Any questions about how we found our eigenspace for lambda equals 1? All right, lambda equals -1, similar idea, -1, -1, -1, -1. So again, same thing, we've lost it off the top of the screen, but we did exactly what we did before, namely plugging in our lambda into this matrix right here. And so I'll go through this one fairly quickly. This is certainly not the first time we've row reduced in this class. And row 2 is row 2 plus row 1. So as before, x2 is equal to t, x1 is equal to -t. Kind of skipped a step there. Let me pop that one back in. x1 plus x2 is equal to 0 from that first row. So x1 equals -t. And so our eigenspace is going to be -tt. Again, same thing we got before. So these eigenvalues and eigenvectors have a nice geometric component. Obviously, they can be handled algebraically as well. We are going to talk a little bit. We'll start that conversation later on today and talk about it a bit more on Thursday in terms of what we can use eigenvalues and eigenvectors for. But in terms of how to compute them, this is basically, we've kind of covered how we actually do the computations, which is just solve the characteristic polynomial to get lambda, plug the lambdas in, and then it's a glorified system of equation. All right, any questions about this example before we try one more? All right, so here's a 3x3. Try and be smart in terms of how do you find your determinant. So I'll give you a couple minutes to get started on finding the eigenspaces for this 3x3 matrix. All right, so if you're already going strong on this question, I know it's a little bit lengthier, so I highly doubt many people are done, if anybody. That being said, for those people who are stuck, I do want to get started. So if you are already moving, going strong on it, keep going and ignore my ramblings. For those of you who got stuck somewhere along the way, we'll start talking about it. So first step, is we have our characteristic equation. So how can we find the determinant of this 3 by 3 matrix? Keeping in mind, obviously, there's many different ways, but we want to make sure that we're doing it in the least algebraically ugly way, so anyone have a good method to find the determinant of this 3 by 3. Because we kind of did one on Thursday and it got really ugly really fast. Yeah, we'll go along column 2. And it's not to say that other methods don't work, but once we start putting variables in here, then all of a sudden, if you start, let's say, even if we had gone along row 1, then you're starting to get a little bit more messy in terms of your calculations. Not that it can't be done, but it can get a little bit more complicated. So really, if you're noticing some zeros, try and take advantage of them. All right, so we get our factor of lambda minus 3, which is nice because we already have one eigenvalue. The rest of it requires a bit more work going on. So multiplying out, that's lambda squared minus 7 lambda plus 10. Multiplying along the diagonal, the off-diagonal entries is minus negative 2. So lambda squared minus 7 lambda plus 12. And how can that last quadratic factor? I kind of gave away that it factors. Yeah, minus 4 and minus 3 would actually meet, which means that we get lambda equals 3, but we get lambda equals 3 twice. And as it turns out, that's going to be important. So we'll say with multiplicity 2. And this is to signify that the factor showed up twice. And we'll kind of see what happens or what could happen as a consequence of that as we move along through this example. All right, any questions about how we found our characteristic polynomial and our eigenvalues? What about negative 5 and negative 2? They aren't eigenvalues. Okay. All right, so we'll finish this off as we did before. Lambda equals 3. We're going to plug that into the exact same matrix we had above. So we'll plug in lambda equals 3 into here and find our solutions. So that's going to be 1, 0, 2, negative 1, 0, negative 2, negative 1, 0, negative 2, 0, 0, 0. And we'll just solve. And again, this is, we're seeing a lot of these system of equations showing up. Obviously, there's quite a bit of calculations involved, but it's nothing we haven't seen for a while. Row 2 is row 2 plus row 1. Row 3 is row 3 plus row 1. All right, so this one can get a little bit strange in terms of we haven't seen a lot of reduced row echelon forms that turned into this. So how are we going to find our solution for this particular system? So this is kind of a new looking one. It's technically not any different than the ones we did before, but it might look a little strange. And in the past, I've certainly seen more errors in questions like this. So what will our solutions be? Do we get any free variables or parameters? How many do we get? And for which variables are they? You got to have an x2. These are things in R3. The matrix has to multiply by something in R3, so x2's got to be there. So again, it looks strange because this column of zeros. Absolutely. Absolutely. So here's where we adhere to our ideas from chapter 1. Which columns give us free variables? In general, which columns give us free variables? In this case, it's going to be columns 2 and 3. Absolutely. In general, which columns give us our free variables? The ones without a leading 1. Well, here is the only leading 1 we have in this matrix, which means column 2 does not have a leading 1. Column 3 does not have a leading 1. So x2 is a parameter and x3 is a parameter. So x2, even though it's just a column of zeros, I mean, really, that just means that that column times anything is still 0. Hence, x2 can be anything. Right. As for x1, the one with a leading 1, well, x1 plus 2x3 equals 0. So x1 is equal to negative 2t. And so our eigenspace, x1 is negative 2t, x2 is s, and x3 is t, where now s and t can be any real numbers. Not R2, just R. But this is definitely the one that I see get done incorrectly the most, and it's because of that column 2. So let's remember our rules. We get a parameter for anything that doesn't have a leading 1. If all you have is zeros, then there's no leading 1. You need a parameter for that. Is people saying x2 equals 0 is probably the most common mistake I see. Because they see column 2, zeros, x2 equals 0. So remember your rules. Parameters for columns without leading 1s. All right, so any questions about how we got our eigenspace for lambda equals 3? All right, for lambda equals 4, same idea. We're going to plug in lambda equals 4 into the exact same matrix. If we do that, we get 2, 0, 2, 0, negative 1, 1, negative 2, 0, negative 1, 0, negative 1, and 0. And then do the same thing, just row reduce, so that's a little bit more boring. But the idea is we're plugging in our eigenvalue into our matrix. As I mentioned on Thursday, and some people mentioned from my pre-lecture videos, what should happen every single time? As I mindlessly drone through the questions here. We should always get a row of zeros, which means, yeah, at least one. So if we don't get a row of zeros, what do we need to do? Or what went wrong? Sorry, I guess is a better way of phrasing my question. That was a bit more meta than I was hoping for in the particular question. The idea here is, again, this is just another system of equations with a different context. But the idea is if we didn't get a row of zeros, either the lambda you got wasn't an eigenvalue, in which case there was something wrong with your solving from the beginning, or it is an eigenvalue, but you made a row reduction mistake along the way. If you do this properly, there should always be at least one row of zeros down there at the bottom. Again, that comes from our list of equivalent statements. Because our matrix is square, the determinant being 0 is equivalent to the reduced row echelon form not being the identity. And so, because it's square, you either have a reduced row echelon form that's the identity, or it has a row of zeros. Again, this is all based off of theory we've been developing since the beginning of the course. Again, that's something special for square matrices. That's not necessarily true all the time. No, you can't intentionally try to make a row of zeros without violating the row operations. It's more just something that should happen during your normal course of row operations. So if it doesn't happen, something's wrong somewhere. You can't really force it. All right. So if you have any more questions about this example, feel free to let me know. If not, I'll give you a minute or two to think about this. I don't want to spend too much time on this, but this is kind of an idea we're going to be using later. So see if you can come up with a reason that if lambda is an eigenvalue of a, then lambda to the k is an eigenvalue of a to the k. And feel free to use for free that the eigenvector stays the same. So if x is an eigenvector, then it'll still be an eigenvector afterwards. If it doesn't happen, then you made a mistake somewhere. Not my problem. This time. No, I'm not saying that I will only give you a matrix where that happens. I'm saying for any square matrix, that is exactly what will happen every single time for any square matrix. So if you find your eigenvalues and then plug your eigenvalue in, you will get a row of 0 when you row reduce. Every single time. It's part of our equivalent statement theorem. All right. So, does anyone have a good reason why lambda to the k has to be an eigenvalue of a to the k? I'm not saying it's an obvious statement, but does anyone have an answer to that? All right, so this is not a calculation question. This is an idea question. So looking at our characteristic equation isn't going to help us very much in terms of what we're doing here, but we're going to kind of have the ideas of what is an eigenvector and what is an eigenvalue. So what is, again, back to what it means, not how do we find it, but what does it mean? What does it mean for lambda to be an eigenvalue of a with eigenvector x? So what does that mean? Geometrically speaking, absolutely. Let's keep it algebraic for this case here, but that's certainly correct. what's equal to a scalar multiple? Yeah. So we know ax is equal to lambda x, and technically we know x is not equal to the 0 vector. Now, that's not what it means. I mean, we're going to see the connection with diagonal matrices as well, but that's not what it means to be an eigenvalue. But that's definitely where we're going to be going right after this example. All right, what do we want to show? We want to show what? So this is what we know, this is what we're given. We want to show that lambda to the k is an eigenvalue of a to the k. So what are we trying to show? What does that mean? What statement are we trying to show? We're trying to show that lambda to the k, so we want to show that a to the k x is equal to lambda to the k times x. So it's hard to show something if you don't know what you're trying to show. We're trying to show lambda to the k is an eigenvalue of a to the k, so this is the equation we're trying to show, because we always kind of want to say, oh, show the left-hand side is equal to the right-hand side. Well, that requires an equation to show this is the equation we're trying to show. So yes, we're trying to show that this left-hand side is equal to that right-hand side, and this is the only thing we can use other than just general matrix properties. That's the only thing that we can use in order to do it. So sometimes showing something is true is just all about knowing what these things mean. And in this case, it's just knowing what it means to be an eigenvalue, knowing what it means to be an eigenvector. That word definition that pops around. All right, so this is what we know, this is what we want to show, and it's all about actually showing it. So let's start with our left-hand side, which is a to the k times x. So we want to show that a to the k times x is equal to lambda to the k times x. And this thing here that I'm about to circle in blue is the only thing we can use. So how could we use that somewhere? How can we use a times x equals something? Because this left-hand side is not a times x. So how can we use that? Take one out? Absolutely. What is a to the k? It's not a value, it's a matrix. What does it mean to do a to the power of k? Yeah, it's a times itself, k times. So a times a times a, k times. So I said this wasn't a times x, but actually it is a times x. It's just a lot of a's times x. And it doesn't really matter the way we put the bracketing because matrix multiplication is associative. It doesn't really matter whether or not we have any brackets. So what's this a times x equal to? That a times x is equal to lambda times x. So a times a whole bunch of a's, and then we have lambda times x. How many a's do we have left? So now we have k minus 1 of these a's and one of these lambdas. Now, unfortunately, this a is not multiplied by x, not beside the x anymore. So is that a problem? That a is not times x. Is that an issue? No, why not? All right, well, perfectly. Lambda is a constant. And now we've written it like this. Now, for those of you who've done discrete math or just in general know induction, this could be much more nicely done as an induction proof. But because I'm not going to assume that knowledge, I'm not going to write it in that form, but for those of you who know that, yes, this could be done as an induction proof. So now we do have a times x, so what do we do with that a times x? What's that a times x? It becomes, once again, another lambda times x. And we just do it again and again and again. How many a's are we left with? K minus 2. And we have 2 lambdas. And then we just keep going. And eventually every single a will just turn into a lambda. So do it k minus 2 more times. There is a mathematical proof that would do that in a much less stupid way, and we would get lambda to the k times x. I don't want to go too deep into making this a perfect proof. Don't really like to write things like do it k minus 2 more times. There's ways of dealing with that better in mathematics, but that's not really the point in this class. All right. So the point here is, and this is the big idea, other than it's nice to be able to work with the definitions and use them for things, but the big thing we get from this conclusion is that if we know something about the eigenvalues of A, specifically what they are, then we can get something about any power of A. And that's going to be, at least in this class, our main application is how can we use these eigenvalues, eigenvectors for powers. And that's where we're going to start in our last section where we're about to get started, is how can we use these eigenvalues and eigenvectors to find powers of A and work with powers of A. And we've already seen one connection. The eigenvalues get raised to the same powers. All right, any questions about these ideas before we start our final section? Don't get too emotional. Don't get too happy either. All right, so I go over this in full details in the pre-lecture videos. Yeah. I go over this in more detail in our pre-lecture videos. So as always, go to the pre-lecture videos for some more of these details. But just to summarize some of the ideas, we call A and B similar. If B and or A can be written in this way, where it's equal to, so P is some invertible matrix. We don't necessarily know what P is. But B can be written as P inverse times A times P, which seems very convoluted. Instead of having one matrix, you have 3 matrices multiplied together, one of which is an inverse, but it has its uses, and that's what our focus is going to be on, how to use these ideas. That being said, if we have similar matrices, they have a lot of the same properties, more than I've written right here. They have the same determinant, they have the same trace, they have the same characteristic polynomial, and the same eigenvalues, which are the ones we're really going to use. That they have the same characteristic polynomial and they have the same eigenvalues. And it's this last one that's going to allow us to diagonalize, which I haven't actually said what that is yet, but I'm going to in about 2 minutes. And obviously the videos does as well. All right, so if matrices are similar, then they have the same determinant and they have the same characteristic polynomial. So let's talk about why they have the same determinant by pushing the right buttons. All right, so if B is equal to P inverse AP, why is the determinant of B equal to the determinant of A? So how can we show that this determinant is equal to the determinant of A? And there's nothing here that we didn't do in chapter 2. Why is that equal to the determinant of A? How can we justify that? Let's be more specific. I absolutely agree. We can split the right-hand side. A bit more specific, how are we splitting up that right-hand side? No, the left-hand side of that is a, I mean, P inverse times P is not equal to the identity. Well, I mean, it is, but they're not next to each other. and matrix multiplication is not commutative. Yeah, so we can split this up. That's the determinant of P inverse. This was a rule about determinants. It was an important rule we saw in chapter 2. That while the order of matrix multiplication cannot be split, determinants can split them up into their products. What do we know about the determinant of P inverse? It's 1 over the determinant of P. And then 1 over the determinant times the determinant. Those just cancel, and we're left with the determinant of A. Unless, of course, we're dividing by 0, but why aren't we dividing by 0? Why can't the determinant be 0? Because P was invertible. Exactly. Right, so obviously this doesn't make much sense to begin with if P was a non-invertible matrix, because even writing P inverse doesn't even make any sense. So, no problems there. All right, so the determinants are equal. The second thing, the one we're really going to be using, is that the characteristic polynomials are equal. In other words, we want to show the determinant of lambda I minus b is equal to the determinant of lambda I minus a. So, can anyone come up with a reason why the determinant of lambda I minus b has to be equal to the determinant of lambda I minus a? And careful, while we could split up multiplication of determinants, we can't split up subtraction. So we can't just write this. That's not the same thing as the determinant of lambda I minus the determinant of b. We can't do that. Can anyone come up with a reason why maybe not even just that, but come up with a reason why, here's what I claim. If B is equal to P inverse AP, then P inverse times lambda I minus B minus A is equal to P inverse lambda I minus B. P. Oh, sorry. Not the P's on the right-hand side. So, I'm claiming this. Can anyone come up with a reason why that's true? And there's no big ideas here. It's just matrix properties. Yeah, exactly. The P's cancel out. That's exactly what happens. So our left-hand side is P inverse times lambda I minus A times P. And we're just going to use matrix properties. Now we know you can't change the order of how we multiply. So matrix multiplication is not commutative, but there is the one that starts with D. Matrix multiplication is what? It starts with a D. It is distributive. So this is P inverse lambda I minus P inverse A. As long as you're careful about which side you're multiplying on, P inverse is on the left, so P inverse has to be on the left. It is distributive. Same thing on the right. So what is P inverse A times P? Yeah, that was our B. What's P inverse? Again, lambda is a constant. It can factor out. What's P inverse times I times P? Yeah, that's just equal to lambda I. So just as before, their determinants are equal. And this is the important one. This is the one we're going to use. So if we have two similar matrices, and that's an if, it's a big if. But if we have two similar matrices, they have the same characteristic polynomial, which means they also have the same what? True, not what I was getting at. They have the same eigenvalues. So if, big if, but if two matrices are similar, they have the same eigenvalues. Now, what's the nicest kind of matrix we can have? And again, I said this was all about raising matrices to powers. A cubed, a to the 5, a to the 10. We know that's annoying. We saw that in chapter 1. Which matrices are easy? That's right, the diagonal. So the idea is if, and I'm going to capitalize it because it's a big if A is similar to a diagonal matrix, then that would say D is equal to P inverse A times P. And what does D look like? What is D going to be? Everything but the main diagonal is 0. What is going to be on the diagonal? More specific than that, based off of what we just talked about. If A and D are similar, what is the same between the two? They have the same eigenvalues. So if A and D are similar, and that's if, and we're going to get to how can we do all of that. That's part of what we'll do next. But if A and D are similar, they have the same eigenvalues. Well, what are eigenvalues of a diagonal matrix? We talked about for triangular, diagonal is an example of that. The eigenvalues are the diagonal entries. In other words, if, still a big if, but if A is similar to a diagonal matrix, then that diagonal matrix's diagonal entries are the eigenvalues of A. And that's kind of the idea of what we're doing here. We want to figure out when we can do this. And that's what we're going to be talking about in our next example. When can we do this? And also, what does the matrix D and what does the matrix P have to look like? So this is the main idea. It is a big if because not every matrix can we do this, but a lot of them we can. And then the diagonal matrix is just those eigenvalues. All right, so any questions about some of these ideas? All right, so here's where I see who watched the pre-lecture videos. This next part is something that I go over in the pre-lecture videos, and just because of time, we can't go through it completely here. But what is P? How do we find the matrix P? So this is not obvious. And it is just something I talked about in the pre-lecture videos. How do we find the matrix P? And it is just some ugly calculations to prove this, which is what I do in the pre-lecture videos. But did nobody watch the pre-lecture videos? Just absolutely nobody? That makes me sad. I spent time making them. Yeah, so P, the columns of P, I know. I know. Where V1 is, I shouldn't say the, is an eigenvector for lambda 1. Oh, I'm not going to ask people to do paid subscriptions. Gross. All right. So we're V1 is an eigenvector for lambda 1. V2 is an eigenvector. All right. Etc. So in other words, to find D, we just find the eigenvalues. To find D, we find the eigenvalues. To find the matrix P, we find our eigenvectors, as columns of V. So those are the ideas, and if we can do this, big if we can do this, then A can be diagonalized in the way we did this. But what's the big problem? Because, I mean, we can always find eigenvalues and eigenvectors. What could go wrong when we do this? So what could go wrong? What's the other thing we need to know about P? Because we have lots of eigenvalues, or sorry, not lots of eigenvalues, but we have lots of eigenvectors. We have infinitely many of them. Can't be hard to get some of them. But what could go wrong with P? And this is where our focus is going to be. What could go wrong with P? Because P can't just be any square matrix. It needs to be what? Yeah. It needs to be invertible. And that's where things can go wrong. That's why I'm saying if this can be done, if this can be done, because we need to figure out exactly when P can be invertible. So that'll be kind of part of the process we see for the rest of today, although we don't have much time, but on Thursday is how do we know when this matrix P is going to be invertible? All right, anyway, so let's get used to this idea. So for each of these three, we're going to see whether the matrix is diagonalizable, kind of why or why not. We'll do the first two today, and we'll see number 3 on Thursday. So 1 and 2, we've done these matrices before, so feel free to go back in your notes. We've done these matrices, so we know the eigenvalues and we know the eigenvectors. So take those answers and see if you can create the matrix D and the matrix P. All right. So for full disclosure, if we were trying to do this problem right from the beginning, the first part of the question would be find the eigenvalues, find the eigenvectors. So that would be the first part of this idea, is we'd have to find the eigenvalues and find the eigenvectors. But just because I want to focus on this new idea first, we're going to take a look at the two examples where we've already found the eigenvalues and found the eigenvectors. But usually that would be step 1 and 2, find the eigenvalues, find the eigenvectors. All right, so let's take a look at this first one. And we should be able to immediately write down D. We should be able to immediately write down D. So what's D equal to? The diagonal matrix, the first one's 2 by 2. So what's our 2 by 2 diagonal matrix? It's going to be 2, 0, 0, and I'm assuming that 5 was meant to be negative 5. All right, so this is our diagonal matrix, 2, 0, 0, negative 5. Where are we getting the 2 and negative 5 from? Right, we're getting those from the eigenvalues, and again, I'm not saying that that's obvious, but that would be part of the calculation. And we've already done that calculation for this matrix. So 2 and negative 5. Great question. Does it matter which eigenvalue goes where? Anyone have an answer for that? Does it matter if I do this or if I do negative 5? I'm assuming the question is whether we can do that. Could we do negative 5, 0, 0, 2? The answer to that is no, but it affects later things. So it depends on the order you're doing. If you're doing D first, the answer is no. If you did P first and then did D, then it matters because of the connection, and I'll get to that in just a second. All right, what is P? So we said the columns of P are the eigenvectors. But we have to be careful here. The first column of P has to be an eigenvector for which eigenvalue? Right, for 2. So if you decided, because it works perfectly fine, to do negative 5 and then 2, change the order, because we just said it didn't matter, you just have to make sure that what you do for P matches up. So if you did negative 5 first, then the eigenvector for negative 5 would have to come first in P. So it doesn't matter which one you do, but you have to be consistent. The first column of one has to match the first column of the other. That's the only thing that matters with the order. All right, so can someone give me an eigenvalue for lambda is equal to 2? And we just need one. We're not finding all of them. We just need one. So one eigenvector. Any of them work. Here's our eigenspace. For example, 2, 1. Bang, 2, 1. Now, you could have done other ones. You could have done 4, 2. You could have done 6, 3. You could have done negative 14, negative 7. Any eigenvalue works. So there's more than one D, and there's definitely more than one P that will work here, if it works at all. All right, what about the second column? What's an eigenvector for negative 5? Negative 1. So some people are saying negative 1, 3. That's great. Another common one would be negative 1/3 and 1. That's fine as well. If you are not scared of fractions, that works just great. I don't know. Got different answers in the chat for this one. Someone asked, where did 2, 1 come from? Anyone have an answer for that? Where did 2, 1 come from? Yeah. So here's our eigenspace. T is allowed to be anything, so just choose, well, almost anything. So just choose a value for T. For example, t equals 1. So one eigenvector would be 2, 1 by taking t equals 1, but you could let t equal anything other than 0 and get a different eigenvector, and any of them would work just fine. Absolutely it does. 4, 2 would work. I mean, makes the numbers bigger than they need to be, but it's certainly nothing wrong with it, and it would also work. All right. So here's P. Is P invertible? Is P invertible? Indeed it is. We could find the determinant of P. We get that it's 7, which is not equal to 0. In other words, this works. And hence 2, 0, 0, negative 5 is equal to P inverse, whatever that would be, times A times P. And we could actually check that. Beautiful. And we could do the same thing for our second one. So I'm going to get to that question, and unfortunately we just don't have enough time to talk about it today, but that's where we're going to start off on Thursday, is what eigenvectors will we put in that would make P not invertible? And that's an important question. Unfortunately, it's not really a question I can answer in 2 minutes. So the short answer to that is, in this example, no, that would never happen. But in some other examples, it could. And we're gonna discuss that. All right, for number 2, not much time left. What would be our diagonal matrix for 2? No, it doesn't matter. You can just take any random eigenvalues. You'll notice for RP, we use t equals 1 for lambda equals 2, but we took t equals 3 for lambda equals negative 5. It doesn't matter. All that matters is that we're getting these eigenvectors. It doesn't matter which one or which value of t that gives to us. All right, so again, the order of these doesn't matter. All that matters is if we did put the 3's first, then the eigenvectors for 3 have to be first. So yeah, so this works, but so would putting these 3's and 4's in whatever order we like, although we do need to have 2 3's. Why do we have to have 2 3's? Right, if you remember back to when we found the eigenvalues, we had lambda minus 3 as a factor twice, so it comes from the multiplicity. So it's important because of that we're putting the 3's there twice. All right, here's where it gets a bit tricky. I'm going to get lambda equals 4 out of the way first. But what can we do for because now we need 2 of them. For lambda equals 3, we need 2 eigenvectors. We need 2 eigenvectors. So can someone give me 2 eigenvectors for lambda equals 3? And remember here, we can plug in whatever we want for s and t. Let's try and keep it simple. So negative 2, 0, 1. This is if I let t equals 1 and s equals 0. Anybody have another one? Again, trying to keep it as simple as possible in this case. So we could let t equals 1 and s equals 0. We get negative 2, 0, 1 and 0, 1, 0. All right. And this I got from t equals 0 and s equals 1. All right. So here we have a p, and this is less obvious, but we could actually figure out this p and see that this is indeed invertible. Why do they have to be different vectors? Great question. Could we have them just be the same vector? Negative 2, 0, 1, negative 2, 0, 1, negative 1, 1, 1. Why not? Yeah, we got to be careful here because we have two columns the same, and if you go back into your determinant Rolodex, if we have any two rows or two columns that are multiples of each other, the determinant turns out to be 0. So in theory, that's not a problem. The problem arises is whether or not P is invertible. So there's no rule against it to create P, except the fact that it makes P not invertible. In fact, it's not just if they're the same. If I took the vector -4, 0, 2, and just took, let's say this came from t equals 2, s equals 0, then that would also be a problem. We would still get the determinant being 0. So that's why, and again, we'll discuss this a little bit more later on, that's why on one of these I took t equals 1, s equals 0, and the other one t equals 0, s equals 1, to ensure that these weren't going to be multiples of each other. And in fact, the textbook talks about something called linear dependence. Unfortunately, that's part of chapter 4, and we don't do most of chapter 4, so I can't really use those words. But the idea is we want to kind of reverse the roles of S and T, because if we end up making these a multiple of each other, or a better word, a linear combination of each other, because there could be more than two, then we could get problems. And we'll talk about that a lot more on Thursday. If you have any questions, please let me know. If not, that's it for today. We'll talk about this a little bit and do a couple more examples on Thursday, but that'll be the end of the course.